messaging used to be, you had to be willing to risk death daily. Orphans were preferred. You got $25 per week for the Pony Express. Messengers since then have not as much of a risky life, but have a lot of things to explain at times. So I'm going to try to do this. My name is Clemens. I work for Microsoft in the Azure team. I'm the architect for all the messaging services that we have. We have some messaging services that are not in our team, but they're in other teams, but we also are generally interfacing with or worked on, and they got then eventually spun out of our team. What's great is that I get 60 minutes today. 30 minutes already happened, because Ben, thankfully, talked about Event Hubs already and about Azure Stream Analytics, because they work exactly like Apache Kafka and the Stream Engine that you just heard about. So KSQL for Kafka, Stream Analytics is a SQL-based language that you can go and use to analyze streams over time. That's this piece. You can use reference tables, so you can use SQL, you can use table storage to go and pull data in that you need to go and refer to. You can do that Stream Analytics. And we also have the ability to take Azure machine learning models and use them in the context of Stream Analytics. Event Hubs is a telemetry stream ingestion system, highly parallelized, partitioned. The great thing about Azure Event Hubs is you don't configure it, you don't deploy it, you don't do anything about it, you just wish one and then one appears. We manage that for you, a completely managed service with uptime guarantees, so you don't need to worry about those things. We also have this. So in addition to just that telemetry pipe that you just saw, we have notification hubs, send one message, and get that automatically distributed as a push notification to millions of devices. This is very popular with news organizations. We have logic apps, which gives you a workflow engine and line of business integration into many different systems, SAP, Salesforce, and also into systems like IBM MQ. We have Service Bus and Azure Queues, which is our queues and PubSub infrastructure. We have Event Grid for event distribution. You'll hear more about that. We have IoT Hub, which is specialized for integration of IoT devices. And then we have the Relay, which does some magic tricks to allow interconnecting sites. So if you have a on-premises pizza store and you're selling pizza and you're selling pizza and you're like a major pizza chain and you are taking orders on your e-commerce site, but you need to go and push those into the site, and you also need to know what the availability is, so you need to have a RPC-like communication. Relay can actually reach into the store without changing the network. So we have a lot of different messaging infrastructure pieces, and the real question is, why do we have so many? Here's some numbers. So these are real production numbers. We just pulled them yesterday. We do 5.1 trillion requests per week in Event Hubs. That's 28 petabytes of data volume that we pull through per month. So that's a petabyte per day that we're pulling through on behalf of our customers. So the average for requests per second is 8.5 million requests, just about. The peaks are obviously much higher depending on where you are. I mean, in European and US peak time, that's a lot more. We run at a request rate that's almost 5 nines, a success rate that's almost 5 nines, which is really good. Also means that we have a lot of failure still with that many events. So there's still work to do, but we're enormously reliable. Our uptimes are also looking like this. Our SLAs are not like that, because you need to have plenty of buffer between what you achieve and what your boss is willing to go and put up some money for. But in reality is we are somewhere between 4 nines and 5 nines in reliability and availability. And really, 80% of our work sinks into that number. On the messaging side, so in Service Bus, we don't do it quite as much as here, because this is a telemetry, high ingest eventing platform. We do about 700 billion requests per month. So it's quite big, and these are some of the largest message broker infrastructures that exist on the planet. So why do we have so many pigeons? Right? Why is there IoT hub and service bus and event hubs? Why do we make so many? Because some will claim, well, you need to have this messaging infrastructure and can do everything for you. That's what we used to believe. That's what we went away from. We started with service bus, and service bus then gained capabilities. What we did in the last 3 years is we started, or 4 years, we started breaking these things apart, and this became this fleet of services, because everything is very different, differentiated, and that's why, that's what I want to explain. And this applies as much to our services as it applies to why is there Kafka and ActiveMQ, right? Why is there Kinesis and SQS and AWS IoT? Like, why do all these different services exist that are just moving data around? I mean, they just move data from A to B. So, there are different reasons why you send messages. So we're going to start with the notion of what is a message. And can we go and classify those further? I don't think this list is necessarily complete. So we have commands, notifications, we have assignments, we have handovers of control to a different process. We have requests, we have traces, we have reports about a condition. These are all different kinds of variations of message. They're all datagrams in some form that you're moving. So how does this help us to get some clarity around what things are? So let's go and create a bit of a structure around those. We're grouping them. Command, transfer, query, handover of control, job, assignment, update, request, versus report, notification, measurement, trace. There's a difference between those. The difference between those is that one group is about intent. One group is about an expectation that I have from another system, either in the form of give me an answer, or in the form of I'm done with my work, I'm transferring control to you, you continue that work. So there's an intent here by sending that message. You have a destination in your mind, where you want to go to. That destination may be something that the process itself is not necessarily aware of, but the implementer who builds that system is aware of it by configuring that flow. So there's an intent behind sending a particular message. The other side were facts, things that have happened in the system and that you report out. There is no expectation that anybody has as they send that message, as they send that event out, that information out, about what should happen with those. And that's the great thing. We're producing information out of a temperature sensor. The temperature sensor just happily reports out its temperature without any notion of what's going to happen with that. So those are messages. Intents, facts. With intents, you have expectations, you create conversations, you have contracts that you form, both in content as well as also mutual behavior. You do control transfers, and you do value transfers. What's also very important, in these intents, you may do a value transfer. What is a value transfer? You do a bank account operation. A bank account operation that you do on a messaging system, that message carries the value. You do a transfer of a purchase order. That purchase order, it's the document that flows in the system that you're passing on. So they actually they carry the value and they transfer the value. And that's also why these messaging systems that are used for that need to be so highly reliable. Because you can't duplicate the information. You need to make sure that it arrives. If it doesn't arrive, then you need to make sure to figure out where it went. Facts convey history. Facts look back at the past. This is process. This is what happened. They have some context. They may have some context, maybe they don't. They maybe have a notion of order. See that within the Kafka presentation, there's a partition, things that are related to a certain context, and they're ordered in time, and you basically scroll over the time order And they have a notion of a particular schema, but no hard behavioral contract between two parties. So those things are different. So I refer to this here as messaging, and we do that. And this area here is eventing. So eventing is where you are moving facts, and messaging is everything else. So that's a relatively clean way to go and separate those things out. Messaging is about relationships. Eventing is about distribution of information. Let's look at events. Events fall into two categories. There are discrete events that are independent, report state change. As Sarah said, they're zero-dimensional. It's the light bulb on or off. That's a state change you may want to go and report out. It's a discrete event. And they're actionable, or at least they're candidates for doing some actions, for doing some work. So if you want to react to the light bulb going on or off that is fired as an event, you take one action. You don't have to go and look at a stream. You don't have to go and look at the, no, it's a discrete thing. Other than a series. The temperature of that light bulb is something that gets constantly read if you have a very smart one. You have a series that's time ordered. A single data point like a temperature reading is usually not very useful. What you want is you want trends. What you want is you want averages. You want to have a computation on top of that. So you're looking at a series of data rather than a discrete state change. So you have a context. Context is that light bulb. You may have, if you have millions of light bulbs, you go and put those, you group them in partitions, and then you can go and pull the data out from particular partitions. And they report typically a condition of something, and they're analyzable. Those events differ in terms of best consumption pattern. What we just saw in the previous talk is that you have a series, and you go in and you provide a context, you pick a partition, and you provide an offset, and you say, I want to read from this point in time on, and then you pull the data towards you. Why do you pull the data towards you? Because you have a stateful compute engine. You have a compute engine that goes and takes a window, computes something over that window, does an average, and then kind of moves the window forward, which means you need to maintain state, which means you need to keep pulling the data towards you. That's why this pull model is really great. Discrete events are different because they're independent. You can very easily push them out. So you can report that out into a serverless infrastructure where none of the infrastructure pieces necessarily is bound together by some state. That means you can build at super high scale a much different infrastructure for discrete events than you can do for serious events, and that infrastructure for discrete events is going to scale better. It's going to compose with modern serverless infrastructure like AWS Lambda or Azure Functions very easily because those events are different. Because you can also scale them out. Here, as long as you have state, as long as you need to pull towards that state, you have a different need for an architecture than for the discrete events. That has consequences. Let's look at some examples here. Sensor readings, as I said, you have a device, you collect the readings, they go into a partition. So that's a very similar picture to what you've seen before on Kafka. You have an analyzer, that's your stream processing platform, that goes in, picks a partition, sometimes is even able to filter down on a stream, picks an offset, and then pulls the data towards it. And then keeps doing that. An alarm from that device, a state change that needs to be reported out, you route that towards an event distributor. The event distributor has subscriptions where the subscriptions can now say, I'm interested in this kind of particular alarm, and those are hooked up to a particular handler and then get pushed out. So you're not running a pump, you're not running a filter, you don't run a process. If that alarm only happens once a day, once a week, you don't need to run any infrastructure for it. You simply have your Lambda function in the case of AWS, or you have the Azure function just sitting there and waiting for that alarm to happen so that it gets triggered and woken up, which means that infrastructure costs you nothing unless that event happens, which is great. Not true for these pulled style event processing things, which always need to work, but true for everything that's alarming. That's why the serverless infrastructure is so great, especially for events that are fairly rare. For commands to devices, you have a device that runs through some cloud gateway, Azure IoT Hub, and AWS IoT are examples for those. And here you have a way to get devices, you can get messages routed through to a backend process, but for each device you have a little queue. You have those little queues because devices pop in and out of coverage of the network. They switch networks, they're roaming, which means if you want to send a message to them, you can't rely on a continuous connection. What you need to have a place that the device can go to and pull data from while it was offline. Now, as long as the device is offline, that queue disappears basically. It has almost zero latency. You send the message in and the data goes straight through so you don't see it. But you need to have a queue here. That model here, specifically with devices, necessitates a different architecture model. Because we have 10 million little queues. If we want to have 10 million devices connected, and 10 million devices is 10 million is a magic number in automotive, happens to be the yearly output of Volkswagen Group, so it's not a crazy number to think about. So connected car needs that sort of capability because cars drive through tunnels and they're disconnected. So you need to have specialized infrastructure that deals with those things. You don't need to have big and heavy queues, but you need to have small things that can go and buffer things up, but they need to be reliable. So that's a different thing. And as you notice, we now added direction. If you want to send commands to devices, you also need to have a path up. These event distribution things capture fact over here and move facts over there. Now we're in the place of messaging where we actually need to go and do bidirectional communication. So IoT Hub and Service Bus do that in our infrastructure. Then you have workflows. So that backend process, which now has information from our device, needs to execute a workflow. Right? You do things. You do things in business, like this is where the real work happens, the back-end work happens. Right? Devices are tentacles of a distributed systems. And here's where the work happens. And you have a workflow manager, formal or informal, or a state machine, or something that goes and processes your work. You have multiple different systems, subsystems, step handler replaced with microservice, and then it's all modern. And then you also need to go and pass that onto, I call this accounting and stuff, but that is standard software that has standard interfaces, SAP, Salesforce, and all those things where you need to have a standardized handoff and some pre-built infrastructure so you don't have to do all that work yourself. So for that, we have logic apps that can go and create these workflows very easily. We have Service Bus, which is effectively an infrastructure, an underlying infrastructure for workflow engines. You can build sagas and all those things on top of it because it's transactional. It maintains state for you for the workflows, so it can do all those things. And Logic Apps also has this whole zoo of adapters for existing applications. And then there's hybrid cloud. Hybrid cloud in two variations. One is the scenario that you just saw Juan do. He said, I use Service Bus. I use Service Bus so I can get back into here. So this was a branch, office or work site, that has an on-premises listener that pulls data off Service Bus. So it's a very fine-grained, very specific route that he sets up. So you set up a topology of routes. You have specific queues assigned to specific sites. You put a message in there, and that pops up in the queue that's assigned to that site, and the site pulls the data back out. there's a firewall in the NAT. We don't know what this network here looks like. So if you want to address the place, you address the name of it in the infrastructure, and then you pull the data out. Database access terminals, RPC calls, documents can be realized over the relay, and the rest over logic apps. And then you have the same picture, a little different, with phones, IoT devices, browsers. I mentioned notification hubs. Well, notification hubs, you also need to get one message out to across the firewall, but using into the shell of the operating system. You need to get a news bit out into your notifications tray in iOS. That requires that you have 10 million registrations, 10 million subscriptions, 20 million subscriptions. We have very, very large use providers who have tens of millions of these subscriptions. You send one message, and then it rolls out into those. That's a wholly different infrastructure. If you want to drive games, we have that. They often use HTTP WebSockets to go and deal with that, to deal with distribution of state of the game. That's yet another infrastructure piece that's not based on that notification hubs thing. It's often using a service bus backplane, and then it's using technology that we call Signal R for the WebSocket last mile bit. So again, very different use case, very different scenario, requiring different architecture pieces. So lastly, we have something that's relatively new. We announced it like 2 weeks ago. So let me talk about that briefly, and then I'm done. So because we need all these different pieces, we saw one big gap in the platform, and that was discrete event delivery. And so we made a new service that's called the Event Grid. And the Event Grid is novel for Azure in that it's not a service that you have to go and set up. You don't have to go and create an event grid for yourself because the event grid exists. What we did is we put effectively a pub/sub layer underneath the entire Azure platform. And all of these different services here raise events, and then you can go and capture those events. To make that a little bit more tangible, I've prepared something. Let's see whether that still works. Probably doesn't. Oh, that's unfortunate. Oh, because, yeah, without network. I didn't know. Microsoft demos, have a good day today. But this one was not out of demo fail, but out of stupidity. Hang on. Let's see whether we can salvage that. There's the portal. So that is perfect. So this is a storage account. So this is not something that is really a messaging entity, obviously, but this is one of our normal services. What we are doing now is we go and take all the services that we have in the platform and grid enable them. And grid enabling means that in the storage account, I can now go and I can obviously also do this over the shell. I have an extension here for the event grid, and I have here a subscription. So conceptually, I tell the storage account to notify me when things happen and push that to a webhook. And the webhook can be anything and anywhere. So here, I have my subscription. I can go and pick the event types, and there are discrete events I blob created, blob deleted, and I want to have them all. And then I can also filter on the container, which means the directory I want to, and I can also say a suffix filter, which means in this case here, I can only ask for like JPEG files. When someone uploads a blob, what happens is that a request gets raised, a message gets raised into that target. So we use request bin, so event grid now goes and pushes out to a request bin the result of me uploading a file, which in this case here is here a blob, and I uploaded the test file. Which means you can now go and build some functionality like if someone uploads a JPEG, start a function, you haven't paid anything until that point, the function will go take the JPEG, scale it down to 5 sizes, store it in a different container, done. That function will never execute again until you upload the next new file. You don't need to set anything up, you don't need to watch anything, it's just driven by that trigger. And so we're going to have those sorts of triggers across the platform for pretty much everything. We're also going to have this for stuff like the queue. So if you have a queue and the queue is empty and the queue is empty for a week, there's no reason to run a process to pull on it. But it's going to raise an event through the event grid that says a message has arrived, and you can react on that and now start your pump to drain the message. Once no longer messages arrive, you let that function go away. So all of those services will also compose. And again, it's just there. It's part of the platform. It's built in, and it's the message-driven composition substrate, effectively, of the Azure platform now. So, summary. A lot of stuff. All of those things have reasons in architecture. It's not just one fits all. We tried that. So we built these IoT hubs and notification hubs, and we built all these things because they all have really rationale in when they and why they should exist. And that list is not done yet. We have more things coming. The great thing is you can also use those for applications outside of Azure. Hybrid cloud means also if you're running an old cranky queuing system somewhere in the corner of your data center, you can use ours with your data center. And that's what I had.